Welcome to our today's class. Our today's topic is more about classes. So we will be delving deeper into the concept of classes in object-oriented programming. This lecture will cover advanced topics such as class type, member variables, parameter passing methods, the use of constant in member functions, inline functions, and static members. By the end of this session, you should have a more thorough and understanding of how to utilize these concepts to write more efficient and maintainable code. Okay, so in object-oriented programming, one of the most powerful aspects is how classes can relate to one another. This connection is fundamental to creating complex, reusable, and maintainable code. So, we have some key points like um, class type, class member variables can be any type, including objects of other classes. If we say like one of the primary features of classes is that their member variables are not limited to primitive types such as integer or string. So they can be objects of other classes. For example, you might have a car class and one of its member variables could be an object of the engine class. This is a crucial concept as it allows us to build complex relationships between objects. So we also have type of class relationships. So by including objects of other classes as members, we establish relationships between those classes. These relationships are the foundation of many object-oriented programming principles. So, such as composition and aggregation. This helps create a modular structure where larger, more complex objects can be built from simpler, reusable components. Then, if we talk about powerful object-oriented principle, this is one of the most powerful principles in object-oriented programming. As it promotes code reusability and clean architecture. The ability to use objects as members enables us to design flexible and scalable systems that can evolve without needing massive rewrites. So we need some special notation for constructors. Why special notation? If we say like when a class has member variables that are objects of other classes, you need to pay special attention to constructors. Constructors are responsible for initializing objects when they are created. So this applies to not only to the class itself but also to any objects that it holds as members. Then calling back to member objects constructor. When the parent object is created, it needs to call back to the constructor of its member objects to ensure that they are properly initialized. This is done through initializer lists or similar mechanisms depending on the programming language you are using. The idea is to ensure that when an object is constructed, all of its parts are constructed as well, leaving the object in a valid and usable state. So this concept is essential for understanding how classes interact and depend on each other, especially when working on large scale projects where classes might represent real world entities, each with their own complex relationships. So you will understand more clearly when you will look at this example. So if you see this example demonstrates how a class type can be used as a member variable in another class. So all the features and all the type classes I just discussed on the previous slide, we will just look at this example. So here we have some key components of the code. First, we have the day of year class, and then we have the holiday class, and then so okay, so we have two classes here, day of year and holiday, and then we will just go through these two classes first, and then we will analyze the code. So the day of year, this class represents a day of the year with two attributes. First is month and day, which is stored as integers, and these attributes represent a specific date. The class has a variety of methods such as constructors, which initialize the object with either a month and day or just the month. Input and output functions, these are typically used for reading input and printing output through so they are not fully implemented here, but these are here for your so to complete the code. So accessor methods like get month number and get day, these two methods are to access the month and day variables respectively. Then we have private members, then we have month and day which are private, and so private means they cannot be accessed directly outside the class. Instead, they must be accessed via the public methods provided. Okay, so that's all for the day of year class. Now inside the holiday class, we have public, where we have this represent a holiday, and it contains a day of year object as a member variable, and a name date. This demonstrates a key object-oriented programming concept, which is composition. Then so what is a composition? Composition is when one class contains an instance of another class. In this case, if you see, a holiday is composed of a day of year object. The holiday class includes its own attributes such as a boolean variable, parking informans, which could represent whether parking rules are enforced on the holiday. The class provides a couple of constructors. The default constructor initialize a holiday to January 1st with parking informants off, and then there is a second constructor which takes three arguments: month, day, and parking informants enforcement, which allows which allows more customizable holiday. Okay, now we will see that the important takeaway from this example is that the holiday class uses a day of year object to store the date information for the holiday. This is a clear demonstration of how class type member variables are used to represent more complex data. This allows for modularity. Instead of rewriting date related logic within the holiday class, the day of year class encapsulates all date related functionality, which allows the day of year class to be reused in other classes or situations where date functionality is needed, which promotes code reusing a code and more maintainability. Now, if you notice that when a holiday object is created, the constructor of the day of year object must be called to ensure the date is initialized correctly. The constructors ensure that all parts of the object, including the member objects, are properly set up when the object is created. These illustrate the need for special constructor handling when working with class type member variables, as we discussed in the previous slide. Well, so this example clearly shows the composition in object-oriented programming, where we can use the structure classes for clarity and efficiency. We can just break down the functionality into smaller usable classes, which can create a more maintainable and scalable system. Okay, so now let's see the main function here. The program starts with the main function, where we create an instance of the holiday class, holiday age to 14 true. This line initializes a holiday on February 14, like Valentine's Day. Then with parking information set to true. So yeah, so if you see, look at the holiday, 14 is the date and 2 is the month, so 14 February is a holiday, and here the true means the parking enforcement set to true. It demonstrates how we can pass parameters for the month, date, and whether parking enforcement is active when creating the object. The message testing the class holiday on line 32 is printed, followed by calling the output function of the holiday class, age.output. The output function will display the holiday details, as we will see in a moment. Here in line 38, holiday and date. So these two lines, 38 and 39, not 39. So this line 38, which this constructor initializes a holiday to January 1st with parking enforcement turned off, which is false. The date 1 part is where the day of year object date is initialized to January 1st, which is crucial since this ensures the object is properly set up when the holiday is created. Then so notice the comment internationally empty. These indicate that this constructor doesn't perform any additional actions beyond the initial member variable assignments. The second constructor on line 41, this constructor takes 3 arguments, month, day, and the enforcement, allowing us to set a custom date and parking enforcement rule for the holiday. It initializes the date member variable with the provided month and day, and sets parking enforcement to the past boolean value. So again, the comment is indicating that this constructor doesn't perform any additional actions beyond the initial member variable assignment. So then on the output function is responsible for printing the details of the holiday. So here this line calls the output function of the day of year class. This demonstrates how compositions work in practice. The holiday class doesn't need to handle the specifics of printing the date. It delegates that responsibility to its day of year member date. So after the date is output, the function checks whether parking enforcement is active. So here if you see on line 48, it's checking if the whether parking enforcement is active or not. So this is a simple if statement that prints whether parking laws are enforced on this holiday. So in our case, since we set parking enforcement to true, the output will indicate that parking laws will be enforced. So then the day of your class constructor, we have on line 54 we have we see part of the day of which is initial must okay. So this constructor ensures that the day of your object is correctly initialized with the provided month and day. It also indicates a call. It also shows like a call test date, which could be a method responsible for validating the date. Now here the interaction between the holiday class and the day of your class is a perfect example of composition. Alright, so if you now look at the test date method, this function is responsible for validating that the values assigned to the month and day variables are legitimate. So first it checks if the month is valid. It prints this ensures the if the month value falls within the range of 1 to 12. So like basic checking if the date format is good or not, which represent the months January to December, and then it prints illegal month value if it's not, or otherwise it exit. Or same with the day, it checks if the date is between 1 to 31. And then the output method, which is designed to print the date in a human readable format. It uses a switch statement where it converts the numerical month value into the corresponding month name, so that that will be easier for human to understand the date format. So it just we have like several more cases, so rest is not shown here. So it will be from January to December. So this is a common pattern for a month, for like 12 months. Then you'll see it's printing testing the class holiday February 14, parking laws will be enforced. So it's printing the outputs from the code. Okay, so parameter passing methods. So how we pass parameters to functions or methods, which has a significant impact on performance and efficiency, particularly when dealing with large or complex data types like class objects. So let's see. So first, if you see efficiency of parameter passing, call by value. When we pass parameters using call by value, a copy of the actual argument is made. This means the function works with the copy, and any changes made to the parameter within the function do not affect the original argument. Then overhead. Creating a copy, especially for large or complex types, can be computationally expensive and lead to increased memory uses. For simple data types like integers or characters, this overhead may not be noticeable, but for class types or large structures, it can significantly slow down performance. Call by reference. In contrast, when passing parameters by reference, the function receives a reference or pointer to the actual argument rather than a copy. This means the function operates directly on the original data, so any modifications to the parameter inside the function will affect the original argument. So there's a difference between call by value and call by reference. So if we say if because if there is no copy made, like we don't make any copy in this method, we just directly do the changes to original argument. So call by reference is far more efficient, and especially when dealing with larger objects, it avoids the overhead of duplicating data and reduces memory consumption. So if we look at here, these two methods, there are like some negligible differences. For simple types, such as integers or characters, the performance difference between call by value and call by reference is usually negligible. The overhead of copying small amounts of data is minimal. Then for class types or more complex data structure, call by reference provides a clear advantage. Um, these types often involve large amounts of data or complex memory structures, and making copies of such data can be costly in terms of both time and memory. Now, in modern programming, call by reference is typically the preferred method for passing parameters, especially when working with large or complex data like class types. The efficiency gained from avoiding unnecessary data duplication leads to better overall performance. If we say additionally, call by reference allows for direct manipulation of the original object, which is often one to update the state of an object within a function. We'll just first finish this, then we will go to that example. So we were talking like what was the constant, okay, what is the constant parameter modifier? So why use constant? Using constant helps create safer code by ensuring that the parameters are not accidentally modified when passed by reference. It also communicates the intent clearly to anyone reading the code. If a parameter is marked as constant, it's obvious that the function will not alter the argument, which can be particularly useful when working in teams on large code bases. So now let's just dive into this slide where constant are with class member functions. So in object-oriented programming, class member functions often work with the internal data of an object. And in many cases, we want to ensure that a function does not modify the internal state of the object. So this is where the constant keyword for member functions comes into play. So on this slide, you can see the general syntax for declaring a constant class member function, where we have type, function name, argument list, then constant. This is the function prototype for a member function that does not modify the object's state. The constant keyword at the end ensures that the function cannot alter any member variables. When we define the function, the constant keyword remains as shown in the function definition box on the right. If you see, type, function, argument list, constant, and then inside we have statements. So when you declare a member function as constant, you are signaling that the function does not and cannot modify any member variable of the class. The compiler enforces this strictly. Any attempt to modify the object state within a constant function will result in a compilation error. So that means all or nothing. So this approach ensures that the function either respects the constantness of the object entirely or it doesn't at all. So there's no middle ground. So when should a function be constant? If there is no need for function modifications, you should declare the function as constant. This is particularly important for accessor functions, which are meant to retrieve the information from the object without altering its internal state. If we say when applying the constant keyword, you should aim to protect all parameters that don't require modification. Not only does this help ensure code safely, but it also enhances the readability of your program, which makes it clear which functions can change the state of an object and which cannot. So it protect all such parameters. Then well, this protection extends to class member function parameters as well. If a member function doesn't need to alter the parameters it receives, you can use constant to ensure they remain unchanged. This also applies to call by reference parameters, as we discussed in earlier slides. Okay, so now in this slide we examine a bank account class with a focus on constant correctness. This class models a simple bank account where the balance is represented by both dollars and cents and an interest rate is applied. Let's dive into the details. So here, if we see the constructors, the bank account class provides multiple constructors for initializing an account in different ways. So first we have bank account double balance double rate, which initialize the account using a balance in dollars as a double and a rate. Then we have bank account integer dollars integer cents double rate. It allows initializing the account balance with separate dollar and cent values as well as an interest rate. Then another one is bank account integer dollars double rate, which initializes with only dollar values and the rate. These constructors provide flexibility in how you create instances of the bank account class. So several of the methods in the bank account class are accessors methods and are declared as constant. So this ensures that they don't modify the object state when called. Now we have void update, void output. So we have void output constant and double get balance constant, integer get dollars constant, and integer get cents constant. And another one is gets double get rate constant. So if we look at those methods, void output constant is responsible for printing the balance and rate of the account. Since it is only meant to display information and not modify the internal data, it is marked as constant, guaranteeing that no changes will be made to the account object. Next, for double get balance constant, this function returns the total balance of the account as a double. Since it is only fetching the data without making any changes, it is also marked as constant. Then get dollar constant and get cents constant. Both of the methods return the dollar and cent components of the account balance. So that's why we made it constant. It marked constant so that we cannot modify anything. Then double get rate constant. Also it It also returns the current interest rate for the account, again because it only reads the value, so that's why it's constant. Okay, now setters. The bank account class also includes setter methods for updating the balance and rate, like void set balance, um, void set balance, void set rate. So void set balance, where first one is with first one parameter, second one is two parameters. So these methods allow you to update the account balance, unlike the accessor methods. These setters modify the internal state of the object, so they are not marked as constant. Also same as set rate, which allows you to modify the interest rate, so it's not marked as constant. So in addition to the public methods, there are some private helper functions that assist with operations such as splitting an amount into dollars and cents, where we have integer dollars part which is constant, and integer cents part which is also constant, integer fraction, a double fraction, integer round. So if we look at these methods, they are likely extract the dollar and cents portion from the double amount, and the round floating number from the round, and for fraction is probably converts the percentage values for to a function. Again, those are marked constant to ensure it doesn't modify the class state. So the bank account class demonstrates effective use of the constant keyword to enforce read-only behavior for methods that should not modify the internal state of the object. So now this design pattern is crucial for writing safe maintainable code, especially in large projects where accidental modification of object data can lead to bugs. So by making methods constant, we ensure that the object state is protected while still allowing access to this information. So now in the main function, which demonstrates the creation of two bank account objects using the objects, and then compares their balances using the is larger function. And if you see here, bank account 1. So if you see the following line 41, a bank account object account 1 is initialized with a balance of 66,543.21 cents and an interest rate of 4.5%. So account 2 is declared, but it will be initialized later through user input. It's not initialized now like the account 1. Now the welcome one, on the next line, welcome function call. So we use this, the welcome function is called with account 1 as the argument. The function will display a welcome message and print the status of account 1. Next, the program prompts the user to enter data for account 2. So here account 2 dot input, so it get the input from user. Then it compare the balance using an if-else statement. So which is larger? So if account 1 is larger or account 2 is larger, it depends on the user input, because account 1 value is already here, we initialized it, but we don't know the account 2 what we are getting from user. This simple comparison will output which account has a greater balance based on the user's input. That's it. So this larger function compares the balances of two bank account objects and returns a boolean value indicating whether account 1 has a larger balance than account 2. So both account 1 and account 2 are passed by reference. This avoids the overhead of copying the objects and allows the function to operate directly on the original data. Both parameters are declared as constant, which guarantees that isLarger will not modify either account 1 or account 2. This is important because isLarger is only comparing the data, not altering the objects. The function compares the balances of the two accounts using the getBalance method, which is itself a constant method, ensuring that no changes are made to the objects during the comparison. So then on inside the welcome, so this is just the welcome function. So it will just show welcome to our bank, then the status of your account is what, I mean whatever it is, it will just output the result. So this is what is this code doing basically. So this part of the code shows how the class prints its data and initialize its member variables. So the output method it just display the account's balance and interest rate in a user-friendly format. So this is the format, the whole format is, so where so since the output function is meant only for displaying data as it's constant, so it's not modifying anything, and it is declared as constant as we declared it constant. So this ensures that calling output does not alter any member variables. And it also begins by calculating the absolute values of account dollars and account cents to handle the display of negative balances properly. So this is done using the abs function. The balance is displayed as a formatted dollar amount. If the balance is negative, the function prints a minus sign before the dollar amount. Otherwise, it is just print the absolute value of account dollars. Now, it also ensured that the cents are displayed correctly, including adding a leading zero if necessary. For example, displaying 0.5 cents instead of just 5. So that's why the whole code is doing just giving a format of your output. Next, we have three constructors for initializing the bank account object in different ways. First one, which initializes the bank account using a single double value for the balance. The constructor breaks the balance into its dollar and cent components using helper functions, dollars part and cents part. After initializing the balance, it calls the setRate function to assign the interest rate. So the second one allows the user to initialize the account with separate dollar and cent values. It calls the setBalance method to set both parts of the balance, then calls setRate to set the interest rate. Then third one, which is initializing the account with a dollar amount and an interest rate, defaulting the cents to 0. It assigns the account dollars directly and sets account cents to 0 before calling setRate to set the rate. So here we will focus on update and input and getter methods like getBalance. Here the first one, like update method, the purpose of this method is like to calculate the new balance based on the interest rate. It starts by combining account dollars and account sets into a single double representing balance. Now the balance is updated by applying the interest rate. The fraction rate function likely converts the interest rate from a percentage to a fraction. For example, it is converting 5% into 0.05, like that. So after updating the balance, the method breaks the total back down into dollars and cents using helper functions dollars part and cents part, which allows the internal representation to continue using separate dollar and cent values. Now the input method. So it is designed to gather input from the user asking for the account balance and interest rate. The user is prompted to enter the account balance as a double. The balance is then broken into its dollar and cents components using the dollars part and cents part function. So then the interest rate input prompts the user to enter the interest rate without a percentage sign. It then calls set rate to store the interest rate properly. This ensures that any input rate is validated or processed according to the internal logic. Next is get balance, get dollars and get cents. All of these methods. First one is get balance, which returns the current balance of the bank account as a double, combining the account dollars and account cents values. This method is marked as constant because it does not modify the object state, simply returns the account balance. So, and the other two, get dollars and get cents, these also return the individual components of the balance, dollar and cents. So this part is just elaborating the set balance, set rate, those functions. So it is basically, the first one is just sets the account balance by taking a double value representing the total balance. It then separates the balance into its dollar and cents component using the dollars part and cents part helper functions. And so these like all of these methods are all like it's just more describing more what that function is actually doing. So I'll just you can also go through and let me know if you have any question. So we'll just go to next slide. So this slide is also the continuation of the previous code, and here we have the cents part and round and fractions, which is just doing their part to so that we can use those. It's just rounding, round means is just doing the floor, and for the fraction is just dividing with the percentage, and cents part is just doing the cents, basically the formatting those areas. Now this is the output for the code. So first it will say welcome to our bank, the welcome message. Then the status of your bank, your account is, then it will show account balance, this one. Then rate, enter data for account 2, it will get input from user. Then if the user input, let's say this one, 12,345.67 cents, then it will say enter interest rate, no percentage sign, then the interest rate is 9. Then it will compare both of these functions, and it will say account 2 is at least as large as account 1. So it will just do the comparison with the interest rate. So that is the output of the whole code. Okay, so now we will explore the concept of inline functions in C++. An inline function is a powerful tool that can help optimize performance, especially for small, frequently used functions. So let's see. Inline function for non-member functions. So for non-member functions, you can declare a function as inline by explicitly using the inline keyword in both the function declaration and definition. So when you use the inline keyword, you are suggesting to the compiler that this function should be expanded directly at each call site rather than making a function call. However, the final decision is up to the compiler. So if the inline functions for class member functions, if the function's implementation is placed inside the class definition, the function is automatically considered inline by the compiler. You don't need to explicitly use the inline keyword in this case. This so if we use the inline functions for very short functions, inline functions should be reserved for very short functions that are called frequently. Typical examples include like getters, setters, or simple arithmetic operations. These functions are prime candidates for inlining because they can reduce the overhead of function calls without significantly increasing the size of the binary. But why use the short functions? Inlining very short functions can make the code more efficient by avoiding the overhead of calling and returning from a function. So next is code actually inserted in place of call. So when a function is inline, the compiler replaces the function call with the actual code of the function at each location where the function is called. This eliminates the overhead of making a function call, such as like saving the program counter and managing the call stack. The removal of the function call mechanism can be more efficient because it eliminates the need for pushing parameters onto the stack, jumping to the function, and returning from it. Instead, the function body is directly inserted into the code, making execution faster for small repetitive functions. Now, while inline functions can provide performance benefits by eliminating call overhead, they come with a trade-off code size. If a large function is inline, it can increase the size of the compiled binary significantly because the function's code is copied at each call site. This can result in slower performance due to increased instruction cache pressure, which is why inlining should be reserved for short, simple functions only. So, this is how it is, how we can use the inline functions. Okay, so now member functions are often defined outside the class definition in a separate file, usually a .cpp file. This keeps this keeps the class header file clean and focused on declarations, while the actual function implementation are placed elsewhere. So but alternatively, member functions can be defined inside the class definition itself. When you do this, the function is automatically considered inline by the compiler. This approach works well for very short functions such as simple getter or setter methods, as I said earlier. By placing the functions in the class definition, the compiler will treat it as inline and insert its code at each call site. So as we mentioned before, it should be reserved for very short functions that are simple and frequently used. So let's go through this example where we have like get balance, the as I said before, getter, setter, this kind of function, short functions is suitable for inline. This function returns the total balance by adding the dollar and cent components, and then get dollars, get cents, get rate, and then inline helper functions, which is dot dollars part, dot cents part, dot fraction, set balance and set rate. So these getter and setter functions are basically inline functions. So in this slide, we'll focus on an important concept in object-oriented programming known as encapsulation. While we have explored the technical aspects of inline functions, it's essential to also consider how the placement of function definitions, whether it's inline or in separate files, it impacts software design, readability, and maintainability. So, if we see, encapsulation is one of the key principles of object-oriented programming. It's sometimes referred to as information hiding or data abstraction. Why it is so important? Encapsulation helps organize and protect the data and functionality within an object. It ensures that an object's internal state cannot be directly accessed or modified by external functions. Instead, access is provided through well-defined interfaces such as like getters, setters, or public member functions. It promotes modularity by separating the internal workings or implementation details. This way, a user of the class only needs to know how to interact with the interface and doesn't need to understand or even care about the internal mechanics. So, why do we separate function, declaration, and definition? One of the reasons we write class function declaration in a header file and definitions in a separate source file is to follow the principle of encapsulation. This way, the user of a class can see what a class is capable of without knowing the actual implementation details of those functions. So, so when functions are defined inside the class, making them automatically inline, the implementation is visible to anyone who includes the class header. This can lead to a violation of the encapsulation principle, as the internal workings of the function are no longer hidden. So the idea of encapsulation is to like you should only need to know the input-output relationship of a function in order to use it. That is, you should understand what parameters to pass to the function and what kind of result to expect without needing to understand how the function is implemented internally. So this is basically the encapsulation. Okay, so think of the class definition as an interface. When designing a class, the class definition serves as an interface for other programmers to interact with. This interface separates the user's view of the class from the implementation details hidden under the surface. The interface should be focused on what the class does, not how it does it. In other words, we can say when a programmer looks at the class definition, they should see a list of function declarations without needing to understand the actual code that implements those functions. So, by thinking of the class definition as the interface, you encourage modularity and separation of concerns. The class interface tells you how to use the class, while the implementation behind the scenes can change without affecting users of the class. So, the problem with writing function definition in the class definition is when you write the function definitions inside the class definition itself, the distinction between the interface and the implementation becomes blurred. Essentially, the user of the class sees not only what the class does but also how it does it, undermining the principle of encapsulation. So, for better style and readability and maintainability, it's generally advisable to separate function definitions from the class definition. This keeps the class interface clean and ensures that changes to the implementation can be made without impacting the user of the class. Alright, so inline function definitions efficiency. So, how the compiler handles inline functions. It treats inline functions differently from regular functions. Instead of creating a traditional function call with stack handling, control transfer, and return mechanics, the compiler replaces each function call with the actual code of the function itself. This special treatment eliminates the overhead of calling the function, which involves pushing arguments to the stack, jumping to the function's memory address, executing the code, and returning to the calling function. When you declare a function as inline, the code for the function is inserted directly at each location where the function is invoked, instead of executing the function from a single location in memory. This is similar to copying and pasting the function code into the main program at every call site. So, for example, if a function is called 10 times in the program, the entire code for the function will be replicated 10 times in the compiled code. What else? Now, so the rule of the, if we go through the, if we talk about rule of thumb, a good rule of thumb is to inline functions only when the function body is about the same size as the function call overhead. This helps ensure that the benefits of inlining outweigh the costs. So now we'll learn about static members. Static members allows data or methods to be shared among all objects of a class. It is especially useful when we want to manage shared data that applies to all instances of a class. So it is like static member variable is a class variable that is shared among all instances of the class. This means that instead of each object having its own copy of the variable, all objects share one single copy of the static variable. Now, since all objects of the class share the same static variable, if one object changes the value of the static member, all objects can see the change. This is because the variable exists in a common memory location that is accessible by all objects. And it can be used to count how many times a certain member function is called across all objects. When you want to track usage statistics or monitor how frequently a function is invoked in an application. And another common use is to track how many instances of a class are currently active. This can be useful for managing resource allocation, debugging or enforcing limits on the number of objects. So we'll see the example for this place keyword static before type. So um, let's just keep this and go here. Okay, you'll see where we use the static keyword before the variable declaration. Before the data type integer, we wrote static, like static integer, static bool. This is how we uh, place the static keyword inside our code. So you will go through this code. This nothing new, just the static. You will go through this example, and here's the output. Alright, so now we have vectors. So vector provides a dynamic alternative to arrays. Vector offers flexibility in memory management, which makes them highly useful in modern programming. Like arrays are fixed size, but vectors are that makes the size grow and shrink, whichever is needed. So, like traditional arrays have fixed size. When you declare an array, you must specify its size at compile time, and once that size is set, it cannot be unchanged during the execution of the time. So if you have 5 elements in an array, if you need to add more elements beyond this limit, you would need to create a new array or find a way to manage. Or if you need one, then the other 4 memory is wasted. Vectors are dynamic, so it can shrink or grow depending on the values. So um, so it doesn't waste memory, or if you need another value to add, you can add, it will grow. So this is how vectors work. uh, you, you can go through this, and